Let's talk about an application of derivatives. One application is motion along a line. So here we have given to us an object's position in meters along a coordinate line given by the equation s of t equals 2/3 t cubed minus 7/2 t squared plus 3t minus 1. We have an equation for position. If we think about taking the derivative of this line, taking the derivative of our position at a certain point in time, well, the derivative is a rate of change. And what is our rate of change as we move through different positions? That is talking about a speed, a velocity. So when we take the derivative of position, we actually get to velocity. What if we were to take the derivative of velocity? Now we're looking at the rate of change of the rate of change. How quickly are we changing in speed? We look at the rate of change of the rate of change, or the change in speed. That is what's called acceleration. And we can continue to take these derivatives. We've talked about this a little bit in earlier videos, how we can continue to take derivatives. We get derivative acceleration is jerk and then jounce, and then it keeps going from there. But we want to remind ourselves of these ideas because these are going to be very important in this problem. So let's look at what we need to be doing. First, the problem asks us to find the object's displacement after 2 seconds. Let's talk about displacement versus distance. They sound very similar, but they are different. In order to talk about displacement versus distance, we really need to start with the discussion of vectors versus scalars. A vector takes into consideration direction. A scalar just looks at the total magnitude. So we need to determine which of these is the vector and which of them is a scalar. The displacement, all it cares about is where we start compared to where we end up. And so it doesn't, we care about how we are getting to that point, where we start versus where we end up. So if we take some turns in there, if we say come down this direction, and then we turn back like this to turn, I'll call this point A, point B, and we come back up this direction, let's say a little bit, get to point C. The displacement is talking about from point A to point C, this red distance right in here. Because we care about where we start and where we end, every turn along the way is important. That means that displacement is a vector. Distance doesn't really care about those turns. All the distance looks like are those initial black lines. This distance here, plus this distance here, plus this distance. So we are ignoring all of those turns. We're just looking at how far we've traveled along the way. And so for that reason, distance is a scalar. Vectors, we care about how we get there, what turns we've taken. Displacement, we care about where we start, where we finish, so how we get there matters. Scalars, we just want to know that total magnitude. Other vectors versus scalars, velocity is a vector. Speed is a scalar. Nice alliteration there, it makes it easy to remember. Velocity cares about direction, so we can have a positive or a negative velocity. Positives moving forward, negatives moving backwards. Speed, all we care about is how fast we're going. We don't care about if we're going forwards or backwards, it's just the total speed. So keep these ideas in mind. So in this first problem, we're asked to find the displacement. This is the one that all we care about is how far we have traveled from where we start to where we finish. Let me clear a little bit of room here. And so we have the equation that gives us the position. What I'm going to do is I'm going to calculate the position after at 0 seconds. And I calculate the position at 2 seconds. Why is it important to calculate the position at 0 seconds? Well, that is my starting point. T is equal to 0 is always my starting point. I don't necessarily start at 0. Sometimes we could be measuring from a different object. So maybe, if this is my house and I'm starting off here, maybe I want my house to represent position 0. because it gives me a good frame of reference. So if I start here, maybe I go back home and then I go off to work and then I go somewhere else. I'm using that house as a central frame. So don't assume that the position at time 0 is equal to 0. We need to calculate this. We're going to do it just by plugging into this equation. So we'll have 2/3 times 0 cubed minus 7/2 times 0 squared plus 3 times 0 minus 1. So if we add all these together, we get -1. Slide over a little bit, -1. I might do the exact same thing for the 2. So we're going to have 2/3, 2 cubed minus 7/2 times 2 squared plus 3 times 2 minus 1. So I'm going to pull out my calculator just to speed me up a little bit through this process. I have 2/3 times 2 cubed is 8 minus 7/2 times 2 squared is 4 plus 6 minus 1. So if we add up all those and then convert this over to fraction, we get -11/3. So if we were to kind of view this on the number line, at t is equal to 0, we are starting at a position of -1. From there, we are actually going backwards to a position of -11/3. To calculate this displacement, we always take wherever we ended up, -11/3 in this case, we subtract wherever we start. So displacement, just write out an equation for this. Displacement is equal to the terminal position minus the initial position. The order matters. With displacement, the order matters because it takes into consideration direction. We care about, are we forwards of where we were, or are we backwards? And in this case, we get a total displacement of -8/3. That means that we have traveled backwards to get to this location. And then if we think about our units, -8/3 meters. We have traveled backwards by 2 2/3 or 8/3 meters to get to this terminal position. So I'm going to just kind of keep track of these answers as I go along. That way we can talk about them. Alright, so -8/3 is our answer for A. And I might have to erase as I go just so I can see my problem. So give me just a second to erase. The problem number, or letter B rather, find the object's velocity after 2 seconds. Alright, so now we need to know velocity. Remember what we discussed at the beginning, velocity is simply the derivative of the position equation. So let me go ahead and calculate the derivative of the position equation, which does give us velocity at time t. We multiply the 3 to the front, we get 2t squared. Multiply the 2 to the front of the next term right here, and we get -7t. And then the derivative of 3t is just 3. Derivative of 1 is 0. So there is my velocity for this problem. I want to know in B, what is the object's velocity after 2 seconds? So I'm going to plug this 2 into my new equation. So we'd have 8 minus 14 plus 3, -6 plus 3 would give us -3. Velocity, what is our unit on this? Well, we probably know from just speeds, we travel in miles per hour, meters per second, whatever the situation would be. And here we do have meters per second. If we think about why that is, it is a rate of change. We are changing the distance, the meters, over a certain amount of time. So that's where we're getting the meters per second. So for B, we get -3 meters per second. Go ahead and clear off some room for the letter C. And so all these calculations, I just keep erasing. This would be what I'd expect to see on your paper. It's just so that we can look at the problem at the same time I'm erasing it. But if I asked you to do a problem like this on your paper, you would just have all of these calculations worked out on your paper. All right, letter C. Find the body's speed after 2 seconds. Well, it's actually going to be that same calculation we just did, right? We found the velocity equation. We plugged in the 2 seconds. We got a velocity of -3 meters per second. But speed is just the scalar of that. And so it's going to be the absolute value. It's going to be the positive. Speed is always a positive. It doesn't care about direction. Could velocity and speed actually be the exact same answer? Yes, they could. If our velocity was positive, it's traveling in that positive direction, they will be exactly the same. But if the velocity is negative, we need to make the speed positive. Speed always has to be a positive. All right, letter D. That one didn't really require any work. Letter D. Find the object's acceleration after 2 seconds. Well, if I need to know the acceleration, I need the second derivative, or the first derivative of velocity. So we multiply the 2 to the front, we get 4t minus 7. So there's our acceleration equation. Acceleration based on time t is equal to 4t minus 7. I want to know the acceleration after 2 seconds, so I'm going to plug that 2 in. 4 times 2 is 8, minus 7 gives me 1. Our unit on this one, well, velocity was meters per second, and now we're looking at another rate of change, so meters per second, which that looks really goofy. How we'd write that is meters per second squared. Acceleration is always measured in your distance measurement divided by your time measurement squared. And so for letter D, we get 1 meter per second squared. Acceleration is also a vector, so you will always keep its sign with it. It does matter if you're accelerating versus decelerating. There's not like a speed equivalent of acceleration. If you were asked for the magnitude of the acceleration, if you want to know just the absolute value of it, you'd be asked for exactly that, was the magnitude of the acceleration. All right, let's move on to letter E. This is going to be the most work of any that we've done to this point. Find the object's total distance after 2 seconds. So just to remind ourselves, how is this different than A? Distance, we care about all those turning points. So if I travel from A to B, and then turn and then go back to C, and then turn and then go up to D, I would need to add up all of these little line segments here. I need to know all of those line segments rather than just saying I've gone from A to D here. Another way to think about this is think about a runner running around a track. I always like to joke this is one of the most pointless activities because once you finish, once you complete however many laps you're going to do, you started here, you end right here. Once you finish, your displacement is 0. You can run all day long and you have a displacement of 0. Of course, that's not what a runner would want to measure, right? A runner wants to measure how far did I travel in my journey. Not the displacement, but the distance. And so they're adding up, well, I traveled 400 meters around, 400 more, 400 more. They're adding up however many laps that they've done. So that's what we need to do here. We need to figure out where did we turn, how far did we go between turns? Well, we don't know where we turned yet. We're going to have to start with that. Let's think about when we're turning. Just if you want to demonstrate this yourself, I would literally just walk around the classroom to show you this. But let's say we start walking and I want to turn the opposite direction. At that instant in time, I have to come to a complete stop. That's the only way I'm going to turn. I have to come to a complete stop. So what that means is the turns will have to occur when the velocity is equal to 0. Turning points must occur when your velocity is equal to 0. Now, are all points where the velocity is equal to 0 a turning point? That is also not true. If you think about coming up to a stop sign, you're driving along, you stop at the stop sign, and then you keep going. Well, you stopped there, you kept going. And that is not a turning point. So we need to be careful that when we are looking at when the velocity is equal to 0, those are potential turning points. Okay, so let's look for those potential turning points first. And we'll talk about how to determine if they are turning points or not. All right, so I'm going to, that's a point, that's a little hard to read. I'm going to set my velocity equal to 0. Remember the velocity equation was a 2t squared minus 7t plus 3. I set that equal to 0. This is a quadratic, so I can factor it. We would always want to, anytime we have a nonlinear equation, we want to factor it in some way. We can use rational zeros theorem. We can use synthetic division. In this case, it is just quadratic, so I can factor as 2t and t. It's going to have to be a minus 3 and a minus 1. So I get t is equal to 1/2. I get t is equal to 3. So then the question is, are these actually turning points? Now, if I'm finding the distance, it really doesn't matter because I can always break up a line segment into smaller chunks. For instance, in this bottom picture right down here, when I'm coming up to the stop sign, continuing and then stopping again, or just looking at terminal position, I can take x and y and add them together, and that would be the same as just adding the whole initial length z. Where we want to be careful is, in this first case where I turned around, we undid all of that displacement. The distances were subtracting in the displacement, so we got back to where we started, like with our track runner. But we have two different amounts here that we need to add for the distance. So again, my point in all this, even if they aren't turning points, we can always break up the interval around these points, and that's just it'll be more work than necessary, but it won't hurt us. If we're explicitly asked for turning points, I need to think about, are these actually turning points? The answer to this is yes, these are both turning points. We have turning points at t is equal to 1/2 and t is equal to 3. Now how could I check that? Well, what we should see if they are turning points is that the velocity is changing signs around them. So for instance, if we have t is equal to 0, we should see that the velocity, if it's positive or negative, is the opposite as t is equal to 1 and then t is equal to 4. We better see those velocities change. So let's just plug these in real quick to prove these are turning points. Take our 0, we plug it into our velocity equation, this equation right here at the top. So it'd have 0 minus 0 plus 3, that's 3. It's positive, that means we're moving forward. Then we plug in our 1, we'd have 2 minus 7 plus 3, that's a negative 2. The velocity is now negative. That means that we are traveling backwards. We have definitely turned inside of that interval. And then finally, if we take the 4 squared is 16, double it is 32, minus 28 is 4, and then add 3 more. If I did all that real quick in my head, it's 7. But again, the important thing there is that we have a positive, and that is telling us that we are traveling forward. And so we can see that the 1/3 and the 3 must be turning points because we saw that the velocities are changing signs from a positive to a negative to a positive. Why is it that these have to be the turning points? Well, they're the only places that the velocity was equal to 0. These are the only possibilities. So we definitely have turning points. Now I did a lot of work there to prove something I could have actually determined very quickly. If you remember what polynomial functions look like, you remember some facts about their zeros. If a zeros or a x-intercept, a root's multiplicity is odd, that polynomial will pass through the x-axis at that point, meaning it would change. Think about passing through the x-axis. It's changing from negative to positive, either way. That is true for odd multiplicities. If we have an even multiplicity, it touches and turns. Notice that both of these ends stay positive. So if we look at these factors, both of these factors occurred once, meaning their multiplicity was just 1. And that means they have to cross through the axis, meaning that they will both be turning points. Okay? So that is how we can determine turning points for a motion along a curve, motion along a line. Now that I have turning points, I'm still not done with the problem, right? I was asked for the total distance, and so how does this help me? Well, we're going to need to know the position at 0. We're going to need to know the position at the 2 still, right? Those are still important. But I also need to know this position at 1/2, because this is, again, this top example here where I've gone a certain amount of distance, I turn, I've come back, I've erased the displacement, I've reduced the displacement, but the distance, I need to add both of these chunks. So I need to figure out how far did I travel here, and then how far did I travel here. That's what I'm looking for. I'm going to essentially take displacements over both of these intervals. All right, so we're going to plug in. I'm going to do this a little bit faster, just do it in my calculator to speed us up a little bit. So I'm going to plug in my 0 first. Well, this one's pretty easy because we had it at the start. It was just the -1. So I know the distance, or excuse me, the position at 0 is equal to -1. Then I'm going to plug in my half. This is the one that we haven't done yet. Let me just start by writing down my answer for S of 2 before I leave that because I erased it from my page. This is one of the downsides to not having it in front of us. It should have been -11/3. Yeah, that would be right. All right, and now I'm going to type in my my equation with the 1/2 plugged in. So we'd have 2/3, and then we'd have our 1/2 to the third power. Notice here I'm plugging these into the initial equation. Why is that? We want to know the distance. The distance is related to the position. We're plugging into the position equation, not the velocity. We know that the velocity at these points would be equal to 0. That's not what we're looking for. We want to know the position at these times. So we have the 2/3 times 1/2 to the third power minus 7/2 times 1/2 to the second power plus 3 times the 1/2 and then minus the 1. So if we do all of that, we should get an answer of should be -7/24. So these positions are just that. They're just positions. We still need to know how far we've traveled between each one. So I'm looking at what was my displacement here, what was my displacement here. And really, I don't care about displacement. That's not quite accurate. I care about the distance between each. We're going to do the same kind of calculation as the displacement, but I'm going to make it positive. So I'm going to take the -7/24. I'm going to subtract the -1. The final position minus the initial. So if I subtract the -1 from this, I get 17/24. Then I'm going to take the -11/3. I'm going to subtract the 7/24 from that. And when we do that, we should get a negative, let me write it out, -11/3 minus the -7/24. We get a -27/8. Again, I don't need the negative. I don't want to use a negative. So for my distance, what I'm going to do is I'm going to add each of these little distances, right? The how far I've gone in each tract. So 17/24 plus the 27/8. I'm just adding the positive version of that. And so when we add these two things together, 7/8, we get 49/12. And so that is our total distance. We need to make sure that we are always including units. And so this would be 49/12 meters. Be a little sloppy with this, draw an arrow, 49/12 meters. So that one was a much larger problem or longer problem than the earlier ones. If we want to figure out that total distance, we have to know where the object turns. We weren't asked for that at the start, so we had to find those turning points first. How do we do that? We set the velocity equal to 0. When we stop, those may or may not be turning points. We've then got to determine that using the multiplicities or by looking at the sign of the velocity on either side of the turning points. Once we know that something is a turning point, we were looking at the interval. We were going from 0 to 2. We were looking at the distance to 2 seconds. We're going from 0 to 2, but we are stopping at 1/2, or we're kind of looking at how far we've gone after 1/2 of a second, so we can add up all of those distances. All right, finally, what is the object's velocity when the acceleration is equal to 0? Let's clear a little bit of room here. We want to know the velocity, but we are not given a time here. We have to determine that time. The time we want to be using is when the acceleration is equal to 0. So we need to actually start with that. I'm going to look for the acceleration equation, which we have. I want that thing to be equal to 0. So I'm going to set it equal to 0. I add the 7 over. I'm going to divide by 4. So at t is equal to 7/4 seconds, that is when our acceleration is 0. I wanted to know the velocity at that time. So now I'm going to take the 7/4, plug it into my velocity equation, which was the upper one over here, the 2 times 7/4 squared minus 7 times 7/4 plus 3. And so let me go ahead and pull out my calculator once again. 2 times the 7/4 squared minus 7 times 7/4 plus 3. When I do all of that, I get the fraction -25/8. And this is a velocity, so our unit is meters per second. So that's our last part there. Don't know what happened there. It should have been, I must have hit a wrong key, -25/8 meters per second. My work has There it is. It's just gone scrunched in with the other stuff. All right, so there is our final answer. And again, because we're asked for velocity, we do want to keep that sign the negative. So this is a good example of how we can use these speeds, we can use these accelerations, how we can use derivatives to find all of these elements. Derivatives give us a rate of change. If we think about a very visual rate of change, that is the speed. Speed can measure distance. It can also measure other things too. It can measure how quickly percentages might be rising or falling, or it could look at how quickly money is changing. And so we're going to see some other examples too. This is not the only example of derivatives. We could be looking at how costs change per unit. Anytime we're looking at a change per unit, that is a derivative. That is a rate of change. So this is just one good example. It's a very visually obvious example, I think, to get us started with how we can use derivatives in real life.